And this is 11.1 chi-squared, good as a fit, the beta lesson. So the example is this. This child makes this die. But it's hard to make this die be fair. You're making something ceramics class. And you would expect, if it's a fair die, you roll it 90 times, then it would come up each of the faces 15 times. It would be really unlikely for that to happen exactly 15 times, even if the die were fair. So here's the distribution. And it says, state the hypotheses, what are the expected counts, and find the value of the chi-square test statistic. All right? So to remind you, this is what is on the template. You need to come up with the conditions, the null and alternate, the test statistic, which in this case would be chi-squared, the degrees of freedom, and the p-value. And then you need to decide to reject or to F2R. Now, if you only do this, as soon as you get the data, you start typing in your calculator, and you skip conditions and null and alternate, your ceiling for the question becomes a 2. Well, you're not going to get your goal by getting a 2 on the inference problem. That's just hairless. So all these PowerPoint prompts are telling you, reminding you to take care of the hypotheses and the conditions and go from there. So the null is that the sides of the die are equally likely to show up, and the alternate is the null. There's the expected counts. Why? Because it's a uniform distribution. In theory, if it's a fair die, you would expect to get 15 of each of the outcomes. You didn't get 15 of each of the outcomes. However, maybe that can be attributed to random variation. And that's why we need to calculate the test statistic. So we'll take just the one. Ready? You got 12 ones in 90 rolls. What do we do with it? We subtract the expected, which was 15, which was 1/6 of 90. That's where 15 comes from. Square it. We have to square it. Why? Because you would get a 0 if you added these up. Because the negatives will work against the positives. And then we divide by the expected amount. So for the 1, we get a 6/10. And we add all of them up, and we end up with 14 and 1400s. I'm sorry, 14 and 4100s. That doesn't mean anything. That's just the chi-squared statistic. We need to compare that to something. We need to compare it to the cutoff. So I'm looking here and saying, all right, if you go to your textbook, now, if you have the electronic copy of the book, I'm not sure how you do this. You go to the very back where the table is. And the table is the very back is T4. So for the die, there are 5 degrees of freedom. And at 5 degrees of freedom, the critical value is 11.07. We compare what we got to this number. But the issue is, this number changes depending on degrees of freedom. It's not like 1.96. That's something that we're just going to memorize. So we look at this number. If, now ready? We could do this on the calculator to get that value. To use the calculator to get the value, we would go here. Remember, there is no non-calculator part of the test. Second distribution, 8. The lower bound for chi-squared, the upper bound degrees of freedom. Okay, so we have 5 degrees of freedom. In fact, let's go this way. Let's go. No, we can't do it that way. We'd have to put in the 1107. So we're going to go here. You have to read the table because you're going to get the table. You're going to see it as it comes up here. Well, coming up. Back to the M&M's problem. Remember the M&M's, there were 60 M&M's, and they did 1,000 samples. They did a simulation. Each of those 1,000 is a dot. And then here's what this looks like from the simulation. What did we get? We get a p-value. Now, ready? That's already given to you, the p-value. We have to go back and get that p-value for the dot. We got a p-value of 0.087. The p-value gets compared to the alpha level. It's bigger than 5%, so we would F2R this. Now, this is different. In a t distribution, we push down on the normal distribution. Depending upon the degrees of freedom. The more degrees of freedom, the less we push down on the normal distribution and the t distribution. But here it's the opposite. The more degrees of freedom, the more you push down on it. And you see what happens is, the larger the sample size, the less skewed chi-squared distribution is. All right? And the mean equals the degrees of freedom. You see from the picture, the center. And the mode would be 2 less than that. So you kind of see it with this green one. Degrees of freedom is 8, that's the center. Where's the peak? 8 take away 2. 4, where's the peak? 4 take away 2. But the mean, ready? The graph's not symmetric, so the mean's to the right of that, right of the peak. So you got a 9.8. Ready? When we did this problem on Friday, is the chi-square distribution. So this is what we were looking for. Here's the 1107. This table, this is the way you would get it. If you don't use the table, which is on your formula sheet, you would literally get some snapshot of some portion of the table. 5% critical value. So what happened? We got 9.8. 9.8 doesn't get there. F2R. On the die problem, ready, we're at 9.8 here. 9.8 for the M&Ms. 14.41 for the die. Both times there were 5 degrees of freedom. There were 6 colors of M&M. There were 6 sides on the die. So if the degrees of freedom stay the same, at the same alpha level, the critical value stays the same. So you see what's going to happen. 9.8 is less than this. You're in the body. F2R for M&Ms. For the die, you're to the right of it. Reject the null because you're comparing it to 11.07. So there's the 14.41. The p-value has got to be less than 5% because it would be 5% exactly at 11.07. So you see the test statistic, 14.41 gives you a p-value of a little more than 1%. Reject the null. Reject the null that the die is fair. Okay? So, conditions. SRS. The sample is less than 10% of the population. This one changes. The expected counts are greater than 5. Now, here's the trick question on the SAT, on the AP test. They give you a problem where one of the observed counts is less than 5. That's got nothing to do with the condition. The condition's unexpected counts. Now, if you did that, which people do all the time, they say, oh, this number is less than 5. You have a blemish on your conditions. You can still get the problem essentially correct. All right. Be sure to examine the expected counts, not the observed counts. There's the test statistic. So here's the other example. You have these hockey players, and they make it to the NHL. And they take 80 NHL players, and they ask them when they were born. And they break the calendar down into quarters. 3 months, 3 months, 3 months, 3 months. So you would expect that this would be a uniform distribution, that you would have 20s across the board. You don't have 20s across the board. Would that be attributed to random variation, or are hockey players more likely to be born in the winter? But no, the birthdays are uniformly distributed. Alpha level's 5%. All the expected counts are 20, all bigger than 5. Okay? We must assume that 80 is less than 10% of all NHL players, which it's not. But if you just said all professional players, you could do it that way. Degrees of freedom. There's 4 quarters, so there's 4 taking on 3 degrees of freedom. We get a p-value of 1.1%. Reject the null. Okay? There is not uniform distribution of birthdays. So here's how you do it. You type in the expected in list 1, the observed in list 2, go to submit test, 3 degrees of freedom, and you get the 1%. And then what happens? You get this list. These numbers add up to the chi-square test statistic. And it's telling you where they came from. So the biggest number came from January, February, and March. That had the highest impact on your chi-square test statistic. Can you write this out? The test statistic, degrees of freedom, and the p-value. And you can see they're the 2 highest numbers. The calculator is giving you those 2 numbers. And that's how we began. Okay? So you're using the template to do these problems. Here is the test statistic. It's the sum of observed take away expected squared divided by expected, which in a sense is list 1 subtract list 2 squared, divide those values by list 2, all right, and add them up. So we're going to send you to 2 separate data sets. Problem 9, problem 13. I have to resume recording. For number 9, of the 6 colors, the null is they're equally distributed. The alternate is they're not. But that doesn't mean that none of them is equal to 1/6. It just means one of them's wrong. But if one of them's wrong, 2 of them have to be wrong. So the alternate is at least 2 of them are not 1/6. Okay? So now what? SRS. The expected count, which is list 2, well, the sample size is 120. Divided by the categories gives you 20. They're all bigger than 5. And there are more than 10 times 120 Fruit Loops. The test statistic is 7.9. But 7.9 is not going to mean anything to you. So if I look, ready? There are 5 degrees of freedom. We're back here. 5 degrees of freedom. The critical value is 11.07. We got 7.9. 7.9 is short of this. If it's short of it, you're in the body and you're going to F2R. We know the p-value, the next line, has to be bigger than 5%. We don't know that unless we can compare the 7.9 to the critical value. So it just happens to be written up there because it's the third time we had the same degrees of freedom to compare to 11.07. Then this 7.9 is the sum of that list of contributions. And it tells you what colors had the highest impact on the test statistic, and it was orange. Okay? Because there were more orange Fruit Loops than expected. Much more. 8 more. Okay? But because the p-value is bigger than the alpha level, the F2R, there's a lack of evidence that the proportions are not equal. That we can say that this could be attributed to random variation. "13. We have these trees, and the birds nest in these trees. So we expect from the past that 54% of the birds in the Douglas fir, 40% in the pine, and 6% in other trees. The alternate is 2 or more are not correct. We have a SRS. Here are the expected counts. The expected counts are in list 2. We multiplied the sample size, 156, times these proportions to get the expected counts. The lowest expected count, 9.36, is greater than 5. And there's more than 1,560 birds. Now what? We only have 2 degrees of freedom now. So if I go to the table in the back of the book to look up degrees of freedom, the critical value at 5% is 5.99. So for the trees, it becomes 5.99, way less than it did for more degrees of freedom. We compared this number. 7.41 is bigger than 5.99. It means you landed in the tail. Reject the null. The p-value is going to be less than 5%. There is evidence that birds have a preference for the trees. Like that's the distribution of the trees that are planted, but that's not how the birds landed in there. They like one tree more than the other. Which one do they like? Well, they like the ponderosa pine more than you expect. The expected number for ponderosa pine was 62.4, and 79 of the birds landed there. Okay? So, if you are at home, You are dismissed to do the exit ticket. We will see you in the building tomorrow. If you are here, 11-2, alpha, beta, gamma, the rest of the week, they would be the chi-square test that you would do in AP Bio.